Hi class, welcome to the next video. We're going to cover chapter 11.2, our next conic section, which is ellipses. Just as a reminder, an ellipse is when we have an angled plane intersecting our conic section. So it is not parallel with the base, and it is not parallel with the slope of the cylindrical side, basically. Okay, so what this what this gives us basically is a stretched out circle, right? So remember, if this was parallel to the base, then we would have a nice perfect circle, but since it's not parallel to the base, it's an elongated circle, I guess is what we can call it, which is an ellipse, right? So we talked about a focus in the last section when we were talking about a parabola. An ellipse actually has two focuses, and the plural of more than one focus is foci, right? So there's two foci. Singular is focus, so there's two focuses. The correct way of saying that is foci, right? Which we call F1 and F2. Okay. If we take any point on the ellipse, anywhere on the outside of this elongated circle, okay, we'll call it P of xy, and we find the distance from that point to one focus and the distance from that point to the other focus, right? So the distance from point to F1 and the distance from our point to F2, if we add those two distances together, it's always the same, no matter what point we choose for our point along the ellipse. Okay, so no matter, so it's always the same value. It's a constant value is really what we should say for that. Okay, so that means that no matter where I am along this this ellipse, this outside of the ellipse, the distance from a focus to the point to the other focus is a constant value. Every ellipse has what's called the major and the minor axis. The major axis is the distance from one end to the long end, long ways, the longest length between one point and its opposite point. And the minor axis is the smallest distance from one end to its opposite end. Okay. And so the major and the minor axis, they all go through the center of the ellipse, right? So we call the major axis kind of the long ways distance, and the minor axis the short ways distance, right? Or the shortest path. So this would be the minor, and this would be the major. Okay. This would be the major, and this would be the minor. So the major and the minor axis kind of tells us, it doesn't tell us the orientation of the ellipse, but it does. It kind of tells us how the ellipse is orientated. So blue is for the major axes in both of these pictures, and the red is the minor axis. So here we have it flush or parallel with the x-axis. Here the major axis is centered or parallel with the y-axis, and here the ellipse has been rotated, and you can see that it does not line up with either axis, but we can see where the major axis is and where the minor axis is. Okay. So the length from the center of the ellipse, okay, the center of the ellipse, to the end of the major axis, so the blue line, so basically half of this blue line here, right, from the center to the end along the blue line, the major axis, is called the vertex. So the end point here is a vertex, and the end point here is a vertex. Both of those together are called the vertices, right? So we say that the distance from the center to one of the ends is a distance of A for the major. Okay, so the length of the entire major axis then is 2A. For the minor axis, we say the distance from the center to the end is B, which means that we have 2B is the length of the minor axis. Okay. The foci are always located on the long axis, on the major axis. And they are equidistant from the center. So if my focus is here for the top portion, then whatever distance from the center to that point to get to that focus, it's the same distance from the center downwards to get to the next focus. All right, and we call that distance C. So let's kind of draw this out with some numbers and some markers and things like that. So if this is my ellipse and its major axis is located on the x-axis, then the end point here would be a0. We're going to consider this as the origin. So I would move a distance of a to get to the end. Okay. I would go a distance of negative a to get to the other vertex or the major axis. Going upwards, I would go up to b, right? And going downwards, I would go negative b. My focus is from here, some distance c away. That means to get to the other focus, I would move a distance of negative c as well. Okay. And then we'll talk about this line here, this dashed dot that connects our focus to the vertex of the minor axis. Okay. So if I draw my ellipse so that the major axis is centered on the y-axis, it looks the same thing. But the difference is that this isn't a distance of b, it's a distance of a, right? So the minor has a distance of b, the major is a length of a, and the focus is always along the major axis, and it has a value of c, and it always lies within my my ellipse. So again, what we were saying before was that if I had a point, let's say here, then the distance from this point to the focus and the distance from this point to this focus, the sum of that value is the same as if I chose any other point and did the same thing. Okay. So coming to these lines here, okay, that go from the focus to the minor axis, right? The focus to the minor vertex. Notice that these create triangles, okay, that have a length of b. Okay, this actually has a length of a, and yes, it is this same a. Length here is c. Okay, so this length a from the edge to the axis is the same as the hypotenuse of this triangle that connects the focus to the vertex for the minor axis. Same thing here, right? Here I have a length of c, I have a length of b, and the length that connects the focus to the vertex of the minor axis is a length of a. And again, yes, it is that same length a from here to the vertex of the major axis. So that gives me a relationship, okay? Because a, based on the equation that we have for an ellipse, two things are going to be very, very easy to find, and that is a and b, okay? C generally requires some work to find. So if I know a and b, I will generally know half of the length for the major axis and the half of the length for the minor axis, or at least where the vertices are, okay? But c is hard to find. But now that we know that this forms a right triangle, we can just use the Pythagorean theorem to solve for c. Right? So remember that we have this triangle, and the values of a and b are how we find the length of c. Okay. So the equation for an ellipse varies really depending on which axis is the major axis and which one is the minor axis. But just like how we found the equation for a parabola, where we connected the lengths from a point on the parabola to the directrix being equal to that point to the focus, I could find an equation for an ellipse by using the same thing, because I know it's a constant value, the distance from the focus to a point to the other focus. I know that that's always a constant value. So I could use that to derive the equation of an ellipse, but I'm not going to. Okay, I'm not going to derive the equation for an ellipse or a hyperbola in the next section. I did it for parabola because it was useful. We don't need to do that anymore. Okay, so just take my word for it, or you can go to the textbook and actually go through the derivation if you really wanted to see it. But we'll just kind of jump into the equation. So the equation for an ellipse tells me right away, the standard form, I should say at least, tells me which axis is the minor axis and which axis is the major axis. Whichever variable has the larger constant under it for the standard form is the one that's the major axis. So if a squared is larger than b squared, then x is the major axis. Okay, and then this would be the minor. If b is larger, then this would be the major axis, and this would be the minor. So when you're looking at these, the equation really, you can really just look at it and say, oh, I know which one is the major axis and which one is the minor. And the square root of this is what that length is. Okay. So we're really just looking for which one has the larger value. On the bottom here, we're assuming that a is larger than b. So if a is the larger value and it's under the x squared term, then x is the major axis and its vertex is at a0, right? If a is the larger value and it's under the y squared value, then the square root of the number that shows up here, or just a in general, is the length of the major axis, and its vertex is at 0a, okay, and 0 negative a. So let's go ahead and do an example. It's easier to use actual values to be able to point this out, right? The word of advice to remember is if our equation is not in the form that we want, then we have to manipulate the equation until it is in the form that we want. Okay, so that's a perfect example for this. Here you see I have 9x squared plus 25y squared equals 225. We are going to find the important parts of this ellipse, the location of the different vertices, the foci, things like that, right? But in order to do this, I need to have it in the proper form, right? So the easiest way to do that is to notice that this is always equal to 1. Okay, you can kind of think of it as like the unit circle, right? X squared plus y squared equals 1. X squared plus y squared equals 1. But I'm dividing those things. So I'm kind of multiplying x squared by some value that's 1 over something, right? Some constant that's 1 over something. So I'm kind of shifting the x's and the y's to make it elongated, right? So I'm shifting all of the x's by a certain amount to stretch it out in x, and I'm shifting all of the y's by a certain amount to shift it out in y. Very similar to what we have when we're in the unit circle and we have r cosine theta and r sine theta, right? As long as those two r's are the same, my unit circle turns into a circle of radius r. But what if those cosines and sines are multiplied by a different value? It turns then into an ellipse, right? So it's basically me stretching out the x by some amount and stretching out the y by some amount is what's happening here, okay? So in order to get this into the proper equation, what I'm going to do is I'm going to divide everything by 225 so that I have 1 on the right hand side of the equation, okay? So divide everything by 1. And look at that, how nice, right? It turns into x squared over 25 plus y squared over 9 equals 1. I have a perfect square on one term and a perfect square on the other. How did I manage to do that? Amazing. Okay. So now that I have a perfect square, which again is not going to always be the case, so don't think that that's what's going to happen. Okay. I need the square roots of these values to determine which one is a and b. Well, this is a larger one, right? 25 squared is a squared, so that means that a is 5. This means that b is 3. So that tells me where my vertices are located. Okay. So that means that on x, from the origin, I go out a distance of 5 to find one vertex, and I go out a distance of 5 in the other direction to find the other vertex. Same thing with the minor vertices. I go up a distance of 3 and down a distance of 3 from the center, and that will tell me where my minor vertices are. Okay. So again, this tells us the major axis is on the x-axis and that a is 5. So plus or minus 5 are the vertices for the major axis. And b equals 3 means that 0 and plus or minus 3 are the vertices for the minor axis. Remember, plus and minus is 2 different values. So this is actually 2 points and this is actually 2 points, right? So if I want to find out where the foci are, I just follow that formula. So remember, this formula was the same for both cases. Okay, A is always the hypotenuse, B and C are just different legs. So if I want to find C, it's always going to follow this formula. Back here. Okay, so again, A is 5, B is 3. So plug those things in, and I get c squared is 16, so that means that c is 4. So my foci are located at plus or minus 4. Just a quick check, your foci should be closer to the origin, or the center at least, than your major vertices are. So my major vertices are at plus or minus 5. My foci are at plus or minus 4. So these are within the ellipse. Okay. So we're going to graph this in just a second, but first let's talk about something called eccentricity. So this is not like an eccentric person, right? This is the eccentricity of an ellipse. So it's a little bit different than when we're talking about people. Okay. So the eccentricity, or what we call E, don't confuse this with the regular E from the natural log or the exponential or the natural exponent. It's not what this is. It is still a value of E, but it's not the same thing. Okay. This E talks about ellipses, right? The eccentricity is the ratio of C over A, or the location away from the center of that the foci is, divided by the distance away that the major vertex is, right? So it's basically the ratio is a relationship, right? How close is C to A, basically? Okay, how close is your focus to your major vertex? It's always going to be between 0 and 1, right? If your focus is at the same exact point that your major vertex is at, that's how we get 1, right? So when these things are equal, we'll get 1. Obviously, C should be kind of closer to the origin. So the closer that C is to the origin, then the closer this value is to 0, right? Because you have a small number over a larger number, like 1 over 1,000, for instance. That's a small value. It'll be closer to 0. The eccentricity tells us how close in the shape an ellipse is to a circle. So if E is very close to 0, right? If the focus is very, very close to the center, then we're more so a circle, right? So if the focus is the center, then we have a circle, because then that means that the distance from every point to the edge is the same, right? It gives us a circle. The closer that we are to 1, the more oblong or football shaped our ellipse is going to be, right? So for our previous example, our eccentricity was 4 over 5, or 0.8. Okay, so we're kind of close to 1. It's fairly oblong. It's more oblong in shape than it is circular in shape. So let's go ahead and look at the graph. So this is the graph of x squared over 25 plus y squared over 9 equals 1. So notice that my foci at 4 and negative 4, 5 and negative 5. Okay, that's based off of this, and it's along the x-axis. Okay, that's my major axis, and those are the vertices on the major axis. Okay, they coincide with the equation. Here we had y squared over 9, so I go down 3 and up 3, and these are the vertices for the minor axis. Let's do one more example. So let's do an application of ellipses. So most orbits in space are elliptical in nature, right? The moon has an elliptical orbit around the Earth. Satellites have elliptical orbits around the Earth. The Earth has an elliptical orbit around the moon. All the other planets have elliptical orbits around the moon. Ellipses are everywhere, okay? Not just in space, right? Obviously, you guys are kind of seeing a pattern here. The last section we did, parabolas, we talked about optics and telescopes and planetary objects, right? Looking at things in space. Right now we're talking about orbits. We're gonna, in the next section, we'll talk about telescopes again, more optics really. But that's one of the main uses, right, of ellipses, is to model trajectories, okay? There's lots of other uses of ellipses. You can look around your house and you can probably see ellipses all over the place. But for right now, we're going to talk about putting something in orbit around the moon. Okay, the point that is closest in orbit to the center of the moon of an object, right? So let's say we have a satellite and we send it around the moon. When it's closest to the moon, it's called the periloon. Okay. And when it's furthest from the moon, right, we're considering it the center, but it still would be the farthest away from the moon in general, it's called the apoloon. Okay. So the center of the moon is at the focus of this orbit on the periloon side. The Apollo 11 spacecraft was in a lunar orbit with periloon at 68 miles and apoloon at 195 miles above the surface of the moon. Assuming that the moon is a sphere, it's not, but let's say that in general it's spherical, right? That has a radius of 1,075 miles. Let's find an equation for the orbit of Apollo 11, right? So this is something that a NASA scientist would do, right? When you're trying to send a satellite out, trying to orbit the moon, trying to do any of the cool fancy stuff that scientists do, okay? So let's think about what's going on here. Let's digest this a little bit before we start to get into math. We are going to say that the center of the moon is at the focus of this orbit. Okay, the orbit is elliptical, so the center of the moon is at the focus. Okay, the Apollo 11 is closest to the center of the moon when it's 65 miles away. Okay, and it's furthest away from the surface of the moon when it's 195 miles. So again, the moon is centered at the focus, but we're talking about the distance from the surface of the moon to the Apollo 11 spacecraft, right? So we have a radius here. So let's go ahead and draw some diagrams. And again, the orientation isn't really very necessary, but we've been talking about things being centered on the x-axis, so that's kind of what we'll do. So like if we look at this, we would think about the center of the moon here, okay? Let's say here, let's draw it a little bit smaller, right? This would be the center of the moon. The satellite is 68 miles away from the surface of the moon when it's closest to the moon in orbit. And it's 198 miles away from the moon when it's furthest in orbit away. Okay, so that's kind of what we're doing. If we're just looking at an ellipse and thinking about the center of the moon being here, okay, right here at this focus. Now we have our own diagram for this, so let's kind of look at that, okay. So we know the length of the major axis is going to be 195. I said 198, but it's 195, okay, plus 68 plus 2 times 1075. So how do we know this? So 195 is from one vertex to the surface of the moon, okay, plus we'll have 1075 to get to the center of the moon, plus another 1075 to get to the other end of the moon, plus 68 to get to the other vertex. Right, so that's a total of 2,413 miles. So again, coming back here, this is the moon. So from here to the surface of the moon, 195. Then 1,075 to get to the center, another 1,075, and then 68. So I just took one end to the other end and I just added up all the distances until I got to the end. And that tells me the length of the major axis. That's what we did here. So from one end, the furthest part of the orbit, to the moon, right, to the surface of the moon, plus one radius, plus one more radius to get to the other side, and then the distance to the other end of the orbit. So that's the length of the major axis. Okay. So what we would do is we would cut this in half, especially if we're considering this to be centered on the x-axis. Okay. Then the vertices of my major axes are plus and minus 1206.5. So me just taking this thing and cutting it in half, because I'm half on one side, half on the other side. So the focus at the center of the moon is going to be located at C equals, so I'm going to take my distance to the edge, okay, and then I'm going to subtract from that one radius plus the edge of the moon. Right? Because remember, the moon is centered at the focus. So if this is the end that I'm at, I'm going to subtract from that the distance to the moon And I'm going to subtract from that the radius of the moon because I know that the center of the moon is located at the focus. So C has to be 63.5. Okay. So C squared equals A squared minus B squared. So what I have already is A, okay, because this is from the major axis. I have my C because they gave me information in order to find the focus, but I don't have B. So if I want to finish solving for B, I have to manipulate this equation so I can isolate B squared. So I'm going to plug in all my stuff, right? So I'll take A squared, this value squared, I'll take my C squared, I'll subtract them, take their square roots, and I will get my C squared. Okay, so that's B squared. So I have X squared over A squared, okay, because I am considering this to be along the major axis along the x-axis, and this is my y squared over the minor axis. Because this was already squared, I didn't have to find the square root, because remember the equation is x squared over a squared plus y squared over b squared equals 1, because I'm putting the longer side on the x-axis. So as you can tell, this is pretty circular in orbit without having to calculate the eccentricity because they are very close in value to each other, right? The difference between a squared and b squared is not a lot.